Well, greetings, Mr. Kolazar's class. Today we're going to start into stoichiometric calculations. So our chapter, stoichiometry, or stoichiometric, would be the actual conversions. And what we're going to look at is our step-by-step problem-solving method for this. And we're going to use this theory of mass to moles, moles to moles, and moles to mass will be our three conversion process that we're going to go through. Depending on where we're going to start and where we're going to end during our reaction for our problems. So to begin with, we're going to talk about the BCE. We'll always need our balanced chemical equation is going to be our starting point so we can have those mole to mole ratios. And we're either going to look at, either how many grams or how many moles can either be produced or needed to react during a chemical equation. So as our chemical reactions are occurring, we're going to be looking at how much we can produce or how much we need in order to react for that reaction to work. So our big steps for calculating is we're going to learn this idea of mass, mole, mole, mass. So that's going to be our big step in our idea. As we're going, each one of these is a conversion. So each of those is going to be a conversion between one unit and another. And so we've done from mass to moles and moles to mass has been our chapter 10 idea. And now we're going to add in our mole to mole ratio from the beginning of 11.1 is where we saw this information at. So as we're going mass to moles, molar mass of A is going to be what we need. Remember, this is from the periodic table. So from the periodic table, we can start out with the moles of A, or to get the moles of A from grams. So if you were to start with any substance, say you had 7.2 grams of helium to start with, then you could multiply it by the molecular mass, or molar mass of helium, 4.00 grams. And our grams could cancel grams, leaving us with moles of helium. So as we're working, that would be our first idea, is to go from grams to moles. Now on the opposite side, if we wanted to look at our conversion, molar mass, once you're in moles, to go back to mass, using the periodic table again, we could convert from moles of a substance, now on the bottom, to the amount of grams of substance on the top, using that periodic table number. Now our new step is going to be that mole to mole ratio from our balanced chemical equation, the BCE. We'll get our mole to mole ratio. Notice our moles of A to our moles of B. A is whatever we're starting with as our starting point, and B is going to be the ending point. So whatever we want to start with versus whatever we want to end with. So the starting one goes on the bottom so our units can cancel, and our B starts on the top. Now these are all conversion factors, so if we think about it, we can set them up all at once to go from the mass of one substance to the moles of it, our mole to mole ratio, and then from our mole to mass. So we're going to be looking at this mass, mole, mole, mass conversion idea. So let's start out with a few problems. We'll kind of quickly go through these. Please, as you go, and if you need to, hit pause so you can get through each part. Remember to be listening up to each part as we're going to help you out as we're going forward. So our question is, how many moles of CO2 is produced when 10 moles of C3H8 is burned in excess of oxygen in a gas grill? So to begin with, we're going to analyze our problem. We're starting out with 10 moles of C3H8 propane, and we're trying to find out how many moles of CO2 are going to be produced. Now, we started with moles, and we're ending with moles of CO2. So our only conversion is just going to be to go from moles of A to moles of B. And we always need to start with the BCE. So to balance this chemical equation, we'll start out with that. 1 mole of propane to 5 moles of oxygen, 3 moles of CO2 to 4 moles of H2O are produced. So step 1, start with what we know. We're given that we have 10 moles of C3H8. Now we're going to set up our mole-to-mole ratio to go from what we have to what we need. In this case, there's 1 mole of C3H8 to 3 moles of CO2. We need to set that up so that our moles can cancel. So moles of our C3H8 on the bottom can cancel our additional moles of 10 moles of C3H8, leaving us then with 30.0 moles of CO2. So in the end, 10 moles of C3H8 are going to produce our 30 moles of CO2. So mole to mole was our first stoichiometric calculation. Similar idea, how many moles of propane, C3H8, are needed to produce 0.5 moles of H2O. So at this time, our starting point, we're given that we have 0.5 moles of H2O, and we need to find out how many moles of C3H8 we have. So our starting point, we're going from 1 mole to another mole, so we're only doing a 1 conversion. So our first conversion, starting out with 0.5 moles of H2O, we're going to move from 0.5 moles of H2O, 1 mole of propane on top over 4 moles of H2O on the bottom. Our 4 to 1 ratio. Remember, no number written in front, we know it's automatically a 1 there. So our moles of water cancel moles of water, leaving us with moles of C3H8. And then one change to make, sig figs. So instead of 0.125, we would round to 0.13 moles of C3H8, since we started with 2 sig figs at the beginning there. For problem 11, what we're looking at is how many moles of carbon is needed to completely react with 15 grams of TiO2, or titanium oxide. So this time, we're starting with 15 grams of titanium oxide, and we're moving to moles of carbon. So we are going to start with the mass of our first substance, mass of A. We're going to go through 1 conversion factor to moles of A, and then a second conversion factor to get to moles of B. So our first step, balanced chemical equation, all we need to change is to put a little 2 in front of our diatomic chlorine. Now our starting point, we said, was 15 grams of TiO2. Now to go from grams to moles, our first step, we need to go 1 titanium times its molecular mass, 2 oxygens times its mass. To add those up, we get 79.90 grams of titanium oxide as its molar mass. Now, grams will cancel grams of titanium oxide, so our first step is now done. Now we're in moles of A. To get to moles of B, we have to look at our balanced chemical equation. Titanium oxide to carbon is a 1 to 1 ratio. So since it's a 1 to 1 ratio, we're still needing to write it. 1 mole of titanium oxide on the bottom, 1 mole of carbon on the top. So our moles of titanium oxide can cancel, and we're left with 0.188 moles of carbon are needed to react with 15 grams of titanium oxide. So we went mass, mole, and then from mole to mole, or the mole-mole ratio. So we did 2 conversions here. 12, similar idea. How many grams of titanium chloride is produced when 2.5 moles of titanium oxide? So our first idea, we need to evaluate our problem. We're looking for grams of titanium chloride, and we're given moles of titanium oxide to begin with. So we're starting out in moles and moving to mass of B. So we're starting here. We need to go through 1 conversion to mole ratio, and our second conversion, moles, to get to our mass of our second substance. So starting out with moles of titanium oxide, TiO2, and what we want to do is our mole to mole ratio. We're moving from titanium oxide to titanium chloride. Should have chose a different one so we didn't have a 1-to-1 ratio, but as we're going, 1 mole of titanium chloride over 1 mole of titanium oxide, our moles cancel our moles, and now we're left with moles of titanium chloride. So we've done our first step, mole to mole ratio. Now to move from moles to grams, we need to use our periodic table. 1 titanium to 4 chlorines gives us an approximate mass of 189.7 grams of titanium chloride. So our moles to moles cancel out, leaving us with grams. Numbers on top are multiplied, divided by numbers on bottom, which we don't need to worry about, and we end up with about 474.25 grams of titanium chloride. Sig fig wise, 475 grams of titanium chloride, starting out with our 3 sig fig values and ending with our 3 sig fig values. So as we're looking, our last step now is going to be to go the entire way. Determine the mass of N2O produced from the decomposition of 25 grams of NH4NO3. So at this time, we're starting out with grams of NH4NO3, ammonium nitrate, and we're trying to find out how much nitrogen oxide is going to be produced, or dinitrogen monoxide is going to be produced. So we're starting out with mass, needing to go 1 conversion to moles, mole to mole conversion to get to the moles of the other substance, and then moles to mass conversion. So to balance our chemical equation, only need a 2 in front of the water. So our step 1 is what we start with, what we know, 25 grams of ammonium nitrate. To go from ammonium nitrate, we first always need to get to our moles, so we need to use periodic table to find out the molecular mass of ammonium nitrate. 80.06 grams is approximate molar mass. So as we're going, our first step, grams of ammonium nitrate cancel grams, leaving us with moles. So we've done our first conversion. From here, we need to go to a mole to mole ratio to go from ammonium nitrate to N2O. And in this case, it's a 1-to-1 ratio. So 1 mole of N2O on top, and 1 mole of NH4NO3 on the bottom. Our moles will cancel moles, leaving us with N2O. And then our last step, we need to go through and get back to mass. So we need our periodic table. 2 nitrogens to 1 oxygen gives us a mass of 44.02 grams of N2O. So moles of N2O can cancel, leaving us in grams. Numbers on top are multiplied, numbers on bottom are divided, and in the end we end up with about 13.75 grams of N2O. If we were looking to go to sig figs, start out with 3 sig figs, we'd end with 3 sig figs. So 13.8 grams of N2O is what we'd see there. And our last problem to work through, this is the one we'll see the mole to mole ratio work through. If we were to start with 25 grams of ammonium nitrate, how much water would we need? Our first step would be, where are we going to start at up top? We're starting out with grams of A. We need to go through a conversion all the way to mass of B, mole to mole ratio, and then moles back to mass. So ammonium nitrate we've calculated out from earlier. About 80.06 grams of ammonium nitrate equals 1 mole. Once we're from mass to moles, our balanced chemical equation gives us that mole to mole ratio. And in this case, 2 moles of water to 1 mole of ammonium nitrate, so that our ammonium nitrate number on bottom can cancel, 1 mole to 1 mole, leaving us with our 2 moles of water on top. And our last step, to go from grams to moles, or excuse me, moles to grams, 18.02 grams of water to 1 mole of water. Moles would cancel moles, and we'd be left with about 11.25 grams of water With our sig figs to begin with, 3 sig figs, 11.3 grams of water would be where we would round to. So as we're going, we used our stoichiometric calculations to answer our mass to moles, moles to mole ratio, and then moles back to mass. Airbags, sodium azide, NaN3, is going to be decomposed to produce sodium and nitrogen gas during a chemical reaction. So what we're going to look at is determine the mass of N2 produced from the decomposition of NaN3 shown to the right. So our first step is we got 100 grams of NaN3. How much N2 are we going to produce during this reaction? So we're starting out with the mass of 1, moving from mass to moles, first conversion, our mole to mole ratio, and then moles back to mass, so that we can go through our 3 conversions. So to balance this chemical equation is where we need to start. 2 moles of NaN3 to produce 2 moles of Na and 3 moles of N2 gas. So we're going to start out with our 100 grams as what we are given here. Mass to mole, our first conversion, 1 sodium to 3 nitrogen, 65.02 grams of NaN3. Once we're there, we need to do our mole to mole ratio to go from sodium azide, NaN3, to 3 moles of N2. It's our 3 to 2 ratio. So mole to mole ratio set up, and then our final step, we have 2 moles, our 2 N2s, 2 N's, so 28.02 grams over 1 mole of N. Moles cancel moles. Numbers on top are multiplied by numbers divided on the bottom. In the end, sig figs, 64.6 grams of nitrogen would be produced, starting with our 3 sig figs. 4 sig figs this time. So we'll keep with the 64.64 grams of nitrogen. In the end, stoichiometric conversions, mass, mole, mole, mass. Again, mass, mole, mole, mass with our 3 conversions there. We'll continue working on these problems.